So a quick agenda here. I'll be talking about a background so that you can understand how this work has come about. Briefly talk about the technical details that form the basis of the work, and then two major applications, which is looking at breathing function and N95 mask breathing, and then also other applications, which I'll just give a few screenshots to look at. So early studies of the respiratory airflow was driven by toxicology studies, and although this shape is quite strange to look at, this is the nasal cavity of a rat, and we're looking that the work here was first done in 1997. And if we look at the mesh here, this is the meshing structure, or the meshing format here are actually structured cells, so which is quite different to what we've seen in recent times, where tetrahedral cells have become dominant, and more recently polyhedrals and polyhexacals. And I guess almost going full circle, and eventually maybe we can look at how we can apply structured meshes in such complex geometries. If we look at the details of technology at the time, this is a HP 735 workstation, and astoundingly, the price is $30,000 for this computer, first introduced in 1992. And if you imagine what we can buy now for $30,000, it would be quite phenomenal. Later, an early study that shifted from the rat nasal cavity and moved to a human nasal cavity was then performed. Again, this is quite coarse in terms of the geometry structure, because in reality these anatomical regions of the airway are much more smoother and highly contoured. Again, if we look at the details of this work, this is 130,000 elements, which is, I guess, if we look back at 1998, is quite phenomenal for that time. And if we look now, 130,000 cells can be simulated in less than a minute, I believe. At the time, the fastest computer was then being used to beat Garry Kasparov in a game of chess. So that's almost looking at the time into the future of what supercomputers could do, and you can see that technology has advanced quite greatly. Okay, so then I jumped in 2005 and eventually published some work in 2006, but we can see here that the geometry is a little bit more realistic. You can see that the geometry is much more curved, and that's possible because of the meshing software that had advanced the field. So beforehand, structured mesh was the only way, but now there was the we used Gambit at the time to do the meshing, and this had a wonderful wrapping and Delaunay triangulation method that allowed us to do the tetrahedral mesh. For those that have a bit of nostalgia, you might look at this and go, oh yes, I remember that, whether it was fond memories or not. At the time, this model was 800,000 cells, steady state, and at the time we were using the K-epsilon turbulence model. We fast forward to recent time, you see now that the anatomical structures of the airway has been improved significantly. Geometry is far more realistic and much more improved, with additional anatomical structures included. So here we've got the sinuses as well as the nasal pharynx, all the way down to the larynx down below. The software has also changed, so we shifted from Gambit meshing to fluent meshing, and now we're looking at 4.8 million cells. It's a polyhex core, and the internal structure or internal hex cells have a minimum volume of 0.2 millimeters cubed in the main airway, and in regions where there isn't much airflow, we can then bump that up to 0.4. The work is transient, and then we applied the SBES model. When we talk about technical details, we firstly have a look at the flow physics, and from the flow physics then determines the modeling requirements of our work. So if we consider the breathing and airflow that goes through the nasal cavity, it is an internal flow. As we breathe in and then out, we've got this oscillating flow, and therefore it's transient. And with that acceleration, deceleration, it's got an inherent unsteadiness to it. And as we're shifting from high breathing to low breathing, the flow regimes move from laminar into turbulent. And you saw before that there's quite irregular geometries. The geometries are quite irregular, highly curved, and not many smooth passageways at all. And this gives the flow significant fluid characteristics, including separation, mixing, and converging, diverging flows. And from these flow physics, we look at the requirements. So for an internal flow, then this is a wall-bounded turbulence problem and has significant near-wall flow behavior. We've got flow fluctuations and frequencies that we need to consider. With the laminar to turbulent flow regimes, we've got the viscous effects dominating and the energy dissipation from the turbulence, and then also boundary layer disturbances and reattachments. So have a look through this. As it's a wall-bound turbulence model, David has already described the significant challenges in producing the required mesh. So in terms of the LES, it's quite stringent and quite restrictive, but the RANS model, such as the K omega SST, is not so bad when we think about resolving the turbulence with RANS mesh. For flow fluctuations and frequencies, because URANS applies an averaging function, it does fail in capturing a lot of the fluctuations properly over time. But LES is also prohibitive, because if we do apply that approach, then the time steps can go down as low as 1e to the -6. And if you consider breathing goes for 4 seconds on average, that's quite a lot of time steps to apply. For viscous effects and energy dissipations, the URANS can provide an overall general picture, but definitely LES is much more superior in capturing these kinds of effects, which include mixing. And we'll see later how important mixing effect is. And for the boundary layer disturbances and reattachments, both URANS and LES can provide sufficient results if we use it correctly. Okay, so from that, our first step into SBES was in 2021, and we applied that to a constant flow rate, and we validated that with some measurements of pressure distribution, and that gave us quite a lot of confidence to move forward. So most recent work here, we've applied the SBES using the LES with whale as a subgrid scale model. I've put here a lot of the details. I won't go through more just because of the time limit, but if you can skim through it quickly, and then if you want the details, I can pass it on to you. The main thing here is to look at resolving the entire flow range or the flow physics over the exhalation and inhalation phases. So here we can see that the whole simulation will go to nearly 6 seconds, and we typically discard the first inhalation phase because of startup effects, where the initial startup has a 0 state, and so yeah, we discard that section. Okay, so I'll move on to the results now, and the SBES allows us to see these really nice structures during exhalation and then also inhalation. So the key message or the key things we find here that there's jet flow behavior, which encourages mixing processes, and that includes moisture transport in the form of water vapor across the mucus. And then there's also heat energy that's transferred between the surface and the inhaled air. Okay, so this picture here is contours of temperature, and this is where the results have revealed some new insights. We noticed that in this pharynx, so this is our pharynx at the back. So this is the front, so for those that are not familiar with this geometry, this is your nostril, and as we breathe in, this contour is a planar slice that cuts through the center of the larynx. So it's hard to get a nice plain picture because there are bony structures inside your nasal cavity that protrude into the airway. So the airway kind of weaves in and out of these bony structures, and hence you never get a nice plain structure or plain profile cutting through that. So the vortex structures, the appearance of them in this pharynx and laryngeal region tells us that there is turbulence occurring there, and it's explained to us that because of that turbulence, then there's increased mixing, and this becomes important for air conditioning. So as we breathe, the air needs to be warmed up to lung conditions, so the air before it reaches the lungs to prevent any damage to the intricate structures down below. I will play this. Let me see. So we see that the cold air enters and that cold air propagates through, and really by the time it gets to the this is your pharynx, the back of your throat, the air is still quite cool, and it really needs to reach 37 degrees before it hits the lung. And this turbulent mixing with the turbulent structures will help to enhance that mixing. And so the new insight from this work was that although the flow is dominantly laminar during the early breathing period, and also the close proximity of the walls provides the high viscous effects to produce laminar flow, there is some compensation for the heat transfer of that due to the mixing in the nasopharyngeal region. When the flow is increased, so flow rate increases, there's enhanced turbulent mixing that occurs in the larynx and trachea, and this provides further heating and conditioning of the inhaled air. The SBES provides the scale resolving simulation results to reveal this mixing effect. So the second application I'm just going to focus on is the N95 mask breathing. We apply species transport to look at the different compositions of inhaled air, which includes temperature, CO2, and the moisture content. The simulation ran for 8 consecutive cycles, and the results here showed that mask breathing increased CO2 inhalation by approximately 7 times more compared to normal breathing. So the simulation here on the left shows again the contours of CO2 where we have no mask exhalation, and on the right hand side we have the mask being worn, and you can see that the buildup of CO2 trapped in the mask is then re-inhaled before it comes back out. So you get that increase in the CO2 exposure. Recent work here we've just finalized for introducing a fan into the mask. So the fan position at the top, fan position on the side, and a fan position at the bottom to allow or to vent out the CO2. And And we find that the bottom fan position of the respirator reduced CO2 exposure by 87% compared to breathing with a mask. And so the SBES model ability to capture mixing processes appropriately is critically important for us to ensure that the simulation is doing the job properly. Okay, so just my final two applications to quickly look at. Here we use the SBES model for spray atomization, and the application here is nasal drug delivery. We want to find out what the droplet size distribution is and its droplet velocities as it breaks up from a liquid sheet. The SBES resolves the surface disturbances that occur on the liquid sheet, and that liquid sheet then continues to break up. We use adaptive meshing to capture the smaller and smaller liquid droplets or liquid ligaments that turn into droplets. And this is also helped by the polymer fluid DPM method. Another application is looking at sneeze droplets. So this was done in the period of COVID. Patients who were presenting at clinics may have their nasal cavities inspected, and that leads to, they may find some irritation in the nose and start to sneeze. So what we find is the nostrils produce two jets, and we look at the evaporating droplets that are ejected during a sneeze. The SBES is important in this case to resolve the free shear turbulence from the two jets that eject from the nostrils. And you can see that these are really nice turbulent structures that are seen with the jet that comes out of the nostrils. We also applied the multi-component DPM tracking to look at the aerosols moving through. I'd like to thank